Please allow me to welcome the paper ID 371, Andrew Mühlenbrock. Andrew Mühlenbrock received his master's degree in computer science in 2019 from the University of Bremen of Germany. He currently is a research assistant at the Department of Computer Graphics and Virtual Reality at the University of Bremen. There he is engaged in the Smart OT project and works on depth sensors, 3D data processing, and visualization and optimization methods. The title of his speech is Optimizing the Illumination of a Surgical Site in New Autonomous Model-Based Surgical Lighting Systems. Dr. Andrew.
Hi, thank you very much for your introduction. Can you allow me to share? Okay, now
Yes.
It works. Okay. So my name is Andre Mühlenbrock. I'm from the Visual Computing Group of the University of Bremen, and I present our paper Optimizing the Illumination of a Surgical Site in New Autonomous Module-Based Surgical Lighting Systems. In open surgeries, good illumination is essential for the success of surgery, for instance, to find tumors and distinguish them from healthy tissue. However, current use illumination methods have major drawbacks. For example, the typical OR lights are able to provide bright light, but often cast shadows and need frequent readjustments. Headlights, on the other hand, are strenuous to wear and require the surgeon to assume a certain head pose in order to direct the light onto a surgical site. There are, for example, also lighted retractors, which are located near the surgical site, but often provide non-optimal lighting, and there are, for example, known cases of burning by optical fiber. So our goal is to create a new lighting method which ensures a constant illumination of the site and is free of shadows. This lighting method should not distract the surgeon, for example, by interrupting them because of light adjustments. Likewise, there should be no collisions between OR lights and of lights in the OR staff. In addition, we do not want to restrict the surgeon in how he has to position his head. And of course, the positive aspects of known lighting methods should be retained, such as safety, affordability, and feasibility. The solution in the Smart OT project, in which we are working with further project partners, is an autonomous module-based lighting system. This lighting system uses many light modules simultaneously, which are controllable in rotation and intensity. And there are depth sensors, which are capable of perceiving the geometry of the surgical stuff, so that we can determine whether the light from a light module would be blocked on its way to the surgical site. Using this information, we optimize the light module intensities to obtain a constant shadow-free illumination at the surgical site. Here you can see a top-down view of the system. And as you see, there are many light modules which have to be controlled in their intensity and rotation. And just for a better idea, a rendered image of our VR simulator of the lighting concept is shown on the right. So, how to detect which light modules are blocked and how to control the light modules by that information to obtain our optimization goals, which are constant bright illumination, which is free of shadows by bodies and heads of surgeons and the OR staff, not to distract surgeons by light changes, and an optimization in real time so that the light reacts immediately to the environment. To solve these challenges, we created an optimization pipeline where the depth images provided by the depth sensors are used as input. By using the intrinsic parameters of the depth sensors, we transform the depth image from each sensor into a 3D point cloud. By using the word registration, in other words, the extrinsic calibration of each sensor in the surgical room, we can project each point cloud, each point onto a common height map. Then we perform multiple occlusion tests of rays between the light modules and the surgical site and calculate a floating point value for each light module of how much light is blocked on the way to the site. We do this efficiently by projecting the rays onto the height map and search along the pixels. Since surgical sites might be deep and we have to be able to illuminate the surgical site in depth, we also perform the occlusion test against the virtual site. For simplicity, we use a tube which is virtually placed at the surgical site, where the hole at the top represents the opening of a surgical site. This way, we know which light modules can penetrate into the surgical wound and which can't. Then we rotate all light modules to the surgical site. Here it is theoretically possible to use multiple surgical sites or other light targets, for example, the table of surgical instruments. And now we use the results of the occlusion tests for each light module to optimize the intensities for all light modules. Our implementation of the intensity optimization allows to smoothly fade between minimizing the number of light simultaneously used as seen on this image and maximizing the number of lights as you can see here. Furthermore, it is possible to set different criteria of optimal lights. For instance, prefer the most perpendicular shining light module or the light module that was unblocked for the longest time. Please read our paper for the exact implementation since there's not enough time for it. And after determine optimal intensities, we temporarily smooth the intensities to not distract the surgeons by too fast intensity jumps. The intensity and rotations after this pass are then finally sent to the light modules. To evaluate how well this optimization pipeline works, we used point cloud recordings of 9 real open abdominal surgeries and simulated our pipeline with it. And as you can see here, ray tests are performed against this point cloud, against this recorded point cloud, and the light modules react to the point cloud. So we have oriented the simulation setup to the characteristics of an actual planned prototype. So we used 56 light modules in a 7x8 grid, where each light module can reach up to 50 kilolux at 1.9 meter distance. Moreover, we placed 5x5 lux sensors in the virtual site, which calculated the brightness at the site at different locations. And we set a target brightness of 80 kilolux at the center of the site. Here you can see a box plot which plots the average brightness over time and over sensors of 9 surgeries. In this case, we used no optimization at all and set all light intensities to the same value, which is needed to obtain the preferred brightness of 80 kilolux at the center of the surgical site. Note here that simply setting all light modules to full intensity would violate eye safety regulations. When we activate the optimization pipeline, we see that we obtain a much better illumination, which is very near to the optimum. Note the preferred 80 kilolux only refer to the center of the site, and we use a realistic light profile, so the optimal average of the light profile is lower. Even if we use only a few optimal light modules, which with much higher intensity, we are also able to obtain a near to optimum illumination at the site. In case of a flat wound, as shown in the right image, the optimization criteria seems not to have a great impact. But let's try in hard case where we have a deep site. When we use all lights simultaneously, again without optimization and occlusion test, barely any light is able to reach the ground of the site, so the average intensity is very low. With optimization, our brightness is way higher. Here we use alpha equals 1. That means as many lights as possible with 3 sites are used. Yeah, I will skip this to time reasons, I think. But you can read our paper yeah, for the results. So we presented a new autonomous module-based lighting system, which we planned in the Smart OT project with further partners. We presented our optimization pipeline, which achieves near to optimum illumination in case of flat site and achieves significant improvement when illuminating deep sites and operates in real time. And currently we are evaluating an actual prototype with our project partners, which uses exactly the presented optimization pipeline we developed. And I can already say this much: both the measurements we are currently performing and the feedback we have received are very promising. So stay tuned, and thank you very much for your attention.
Thank you very much for your excellent speech. Thank you, Andrew.
You're welcome. Thank you too.
Thank you. If there have any questions, please feel free to ask. Maybe there are no questions. Thank you, Dr. Andrew. See you next year. Goodbye.
Goodbye.
Next, let me welcome